Good afternoon and welcome to this webinar, Your Profit is on the Line. This event is brought to you by Quality Magazine and sponsored by DataNet Quality Systems, Integral Concepts, and WinSPC. I'm your moderator, Maggie McFadden, Managing Editor of Quality. Thanks for joining us. Today's presenters include Allise Wachs, President of Integral Concepts. She has 20 years of experience in the application of statistical methods to optimize manufacturing processes and product designs and to assess product liability risk. As president of Integral Concepts, Wachs assists manufacturers in the application of statistical methods to reduce variation and improve quality and productivity. Dr. Wachs holds a bachelor's degree in mathematics and statistics, a master's degree in statistics, and a master's degree in industrial and operations engineering. She also holds a Ph.D. in operations research, all from the University of Michigan. Also presenting today is Frank Tappan, Vice President of Solution Delivery at DataNet. Frank has more than 20 years of experience in manufacturing quality control, statistical process control, and software integration. At DataNet, Tappan leads a team of engineers who assist manufacturers in designing quality programs and implementing real-time quality control solutions. He is a certified quality engineer, certified quality auditor, Six Sigma Black Belt through ASQ, and holds a bachelor's degree in computer science from the University of Michigan. The final presenter today is Stephen Wachs, Principal Statistician of Integral Concepts. Stephen has extensive experience in the development of statistical models, reliability analysis, designed experimentation, and statistical process control, including work as a statistician and Six Sigma Black Belt at Ford Motor Company. Wachs has a Bachelor of Science degree in Mechanical Engineering from the University of Michigan and an MBA from the University of Pittsburgh, as well as a Master's in Applied Statistics from the University of Michigan. Before we begin the presentation, I just have a few housekeeping items for you to have an effective webinar experience. You'll notice to the left of your slide area there is a resource box. This allows you to click Help in the case of technical difficulties. You can also enlarge slides if the font is too small for you, or download slides to print out a copy of today's presentation. You can also invite a friend to join you. If you need additional assistance, you can always click email and a message will be sent to us at webinars@bnpmedia.com. Above the resource box, there is a blank questions box that allows you to type a question and then hit the Submit Question button to send it to us at any time during the presentation today. Later in the live program, our presenters will address as many of these questions as possible. Today's event is being recorded and archived on QualityMag.com, and all registered participants will receive an email within 1 to 2 business days that has a link to view a recording of the event. And now I'm excited to turn over to today's first presenter, Allise.
Thank you very much, Maggie, and thank everybody who's attending also. So we're here to talk about how your profit is on the line. And what we're here to do is we're going to talk about 5 practical steps that manufacturers can take to make the highest quality products for the lowest possible cost. So today's agenda includes achieving growth and prosperity through manufacturing excellence. We're going to move from there, and we're going to talk about quality, two aspects of quality, essentially. We're going to talk about robust design, and then we're going to talk about manufacturing operations and how variation in manufacturing operations affects quality so deeply. Then finally, we're going to give you 5 practical steps that you can take for manufacturing excellence. Now, quality is a sound investment. I want to talk about the traditional view of quality, which has basically been more quality control. And by that I mean making sure that when we make bad products that we control and contain them so that customers don't get them. But a much more progressive view of quality is that it's a competitive differentiator. Basically what it does is it creates customer loyalty. It stops competitors from competing with us, and then it also gives us the ability to charge higher prices. Investment in quality reduces costs, and it reduces them dramatically. So I want to talk about where manufacturing quality problems come from and some of the costs associated with them. So first of all, with manufacturing quality problems, we have lost market share due to unsatisfied customers, and that's a huge cost that is very often not accounted for. Also, we have high levels of plant scrap, so internal waste. We've been in and out of hundreds of manufacturing plants, and in our experience, many of them have extremely high levels of internal waste. Now, because they have so much internal waste, an additional cost that they have is high inspection costs, because they know that they're going to make bad products. Now they have to put systems, people and automated systems in place to make sure that they catch all that scrap. We also experience, unfortunately, catastrophic product failures. So when products fail in the field, that leads to huge problems. Obviously, we have customer complaints, we have lost business, we have warranty, we have recalls, and a serious aftermath is litigation. So often we testify as expert witnesses into causes of failure, and many of these lawsuits well exceed $100 million in penalties. So we're talking about a lot of money on the line. I want to move there to talking about losses in profit. Right now, everybody's hearing in the news about the Toyota recall. It's making big news. But I think what hasn't made the news and what should also be making the news is over the past 40 years, there have actually been 77,000 automotive safety recalls. And that's just in the United States. That excludes the rest of the world. Another important statistic to understand when we talk about losing money is that the U.S. auto industry spent $14.5 billion on warranty in 2008 alone. So net profit is usually only a small percentage of revenue. So when we think about how much is warranty really eating up of our profits, very often it's eating up at least half of our profits. Just talking about recall costs of consumer products, where we're not going to talk about automobiles, consumer product recalls exceed $700 billion a year. So when we talk about making an investment in quality, these investments in quality are very, very small relative to the potential gains that we can have. Now, when we talk about investing in quality, there are two basic areas that I want to talk about. The first is product design. And in product design, we should be very quickly developing new products so that we can get to market first, but we also want to be developing these products to be highly robust, and by that I mean they work in a wide variety of environments, but also we want these products to be highly reliable. And what we see from our excellent manufacturing clients is that they develop predictive models that actually predict product performance and actually predict time to failure of their products, so that they know in advance how their products are going to perform in the marketplace. I'm just going to give you a simplistic example of how you can do something like that. So imagine that you're designing an automotive window and door system. All right? There are a lot of things that you're going to need to take care of. For example, you're going to want to make sure that the wind noise is not too great. You're going to want to make sure that the door closing effort is reasonable. You're going to want to make sure cosmetically that the margins, the seals, the flushness, the gaps, and all that looks really nice. Also that you can cycle the door to failure and know what kind of performance you're going to get or how long the door system is going to last. What these great companies do is they actually have physical models that predict what the wind noise will be, what the door closing effort will be, what the gaps are going to be, and so on and so forth, for all the design variables, like the material choices we make and also the dimensional choices we make, so that as we're changing dimensions, we can actually see the effects on wind noise, door closing effort, and so on and so forth. So that's where we see the excellent manufacturers stand out, at these developing these physical models that predict performance. Now, the second issue, once we have a good design, is we really need to think about minimizing variation. And again, we can deploy these physical models again, and these physical models should be predicting process performance. So instead of product performance, process performance. And as a result, we should be knowing where to be setting temperatures and line speeds and pressures and things like that. We have to think about using statistical process control real time to be able to detect changes that might occur during manufacturing operations. So we have to be very data-driven here and understand that the variables in our models actually are going to need to be controlled, and we can use SPC effectively to do that. In order to figure out which characteristics are important, we rely on these physical models to tell us which are the most important predictors of performance, and those are the characteristics that we should be monitoring in real time. And I can give you an example. One example is that in litigation, very often we see that something like, I'll give an example, like a rear differential unit or a transmission system, which has been performing fine in the field with no issues whatsoever. All of a sudden, customer complaints come in, let's say, about this transmission system, and then we have a huge warranty issue come in and huge customer complaints coming in. What happens is when this goes to litigation and we go back to the plant and start discovering data and information, we extract data that nobody ever bothered to look at real time. But when we do extract that data, very often what we find is there was a statistical change in the process, right, that coincides just with the time when all the customer complaints begin. Had these companies been using SPC real time, they would have been able to detect right away the statistical change and prevent the huge issue that ensued afterwards. So I want to go into talking about 5 practical steps that you can take to make sure that you have this high quality and manufacturing excellence. And the first step is to prevent rather than to react. So when we prevent, then we can really eliminate our scrap, rework, warranties, repair, customer complaints, things like that. We also can improve our quality, our reputation, our competitiveness, and our profitability, which is really, really important. So I want to go in and I want to talk about prevention tools. There are some traditional prevention tools, and they tend to be more on the qualitative side. So things like failure modes and effects analysis, FMEA, mistake proofing, cause and effect, brainstorming, things like that. However, I want to see people, and basically the world-class manufacturers, use much more progressive prevention tools. Those progressive prevention tools include data-driven things like real-time statistical process control, design of experiments, reliability, statistical modeling for prediction, hypothesis testing, multi-response optimization, and so on and so forth. So there are so many quantitative tools available that help us. So some practical actions that we could take is be applying these methods during product development so that we can be predicting performance. And a typical tool that we can be using is design of experiments or reliability analysis and testing and regression models in the product development stage. Also, we should be applying these methods during process development so that we can also be predicting process performance. In addition, when we have problems, we can very quickly deploy these tools as well to very quickly resolve issues. We should be leveraging these predictive models to achieve robust designs, highly reliable designs, and make sure that our specifications are right on. One disturbing statistic that we see in our practice is that over 90% of failed products actually meet specifications. So somehow there's a weakness in how we're setting specifications. So as we design products better and use these models, they help us. And then finally, we should be using real-time statistical process control to monitor and alarm people so that we can prevent issues instead of waiting around. The next thing I want to talk about is properly applying SPC. So this is another practical step that we can take. Now again, world-class manufacturers properly apply statistical process control and get enormous benefits. The first thing, though, we need to understand is we need to understand the purpose of statistical process control. So the goal of SPC is to detect changes before we're actually making unacceptable product. A misconception is that the goal of SPC is just to detect unacceptable product, but that isn't. Okay, it's to detect changes before we're making unacceptable product. And we talk about stable processes or in-control processes, and what do we mean by that? What we mean is that imagine that we're manufacturing something, we're looking at a dimension such as outer diameter. If I look at outer diameters at one point in time and I look at the distribution of those outer diameters, if later on in time I go back and look at those outer diameters or the distribution stayed the same, then I say the process is in control or outer diameters are stable. Okay? When we have that stability or in-control process, at that point we can make a lot of predictions. We know what to expect of it and we can predict. On the other hand, in the lower right-hand corner, you'll see a graphic where, let's suppose that the first 2 times we look at outer diameters, they look consistent, but the third time we go look, the outer diameters are following a different distribution. We say the process is out of control because we see unexpected behavior. Now, even if all of these outer diameters are still within specification, we should expect changes in product performance. So I know that's hard sometimes to understand, but we see that all the time. I want to talk about the difference between stability and capability. So SPC's whole goal is to address the issue of stability, see whether we're stable, and if the process changes, the idea behind SPC is that we'll detect the change right away. The other issue is capability, and what I mean by capability is the ability of a process or a product to meet specifications. Capability and stability are often confused with each other, but they're actually independent of each other. Stability does not imply capability, and nor does capability imply stability. And that's why in that graphic you see any one of the four situations are possibilities. And I'm going to move and talk about then, if you do want to apply SPC, what are some of the supporting methods? Before we even look at data in general, whether it's for SPC or any kind of analysis, we should really look at our measurement systems. All measurement systems are subject to error or variation, and we need to make sure that we're not getting too much error in our measurements so that if we are, we need to fix that before applying an SPC program. The other thing is that in most industrial processes, there are probably millions of variables that affect performance. So we really need to focus on using tools that help us quickly hone in on the few key variables that really do affect product performance. And the most effective tools that we see are the use of design of experiments, regression, statistical modeling, and so on and so forth. Now, another misapplication of statistical process control is that we select an inappropriate chart. Basically, the common X bar and R charts or the individuals and moving range charts, those were charts that were developed back in 1920s. And back in the 20s, industrial systems were much more simplistic. They tended to be slower in speed and so on and so forth. Nowadays, production systems can be quite complex, very high speed, and they have a lot of issues associated with them. We really shouldn't be using some of these traditional charts for many modern-day production systems. Again, world-class manufacturers understand that they need to pick the right kinds of charts for the right application, and there are dozens and dozens of SPC charts that have been developed to handle modern-day production systems. You can see a slight graphic of one that monitors two sources of variation, cavity to cavity or spindle to spindle, also over time variation, things like that. So we have more progressive tools. Now from there, I also want to talk about a little bit more about chart selection, and that is we have very different kinds of production systems with regard to some production systems are very unit-oriented. I make a part, I make another part, but others are much more batch system or even things that are continuous processing like extrusion processes. For many chemical processes or even extrusion processes, things like QSUM charts, tabular QSUM charts, or even exponentially weighted moving averages charts might be more appropriate charts for those kinds of applications. Now, another issue that we need to address is sample size. Again, world-class manufacturers know how to pick proper sample sizes to be able to detect the kinds of changes that they need to detect. So if we have inadequate sample sizes that are too small, our process might change considerably, but we're not even going to know about it until it's way too late. We can also make the opposite mistake, and that is have sample sizes that are too large and then detect changes that are really not practically important, even though they might be statistically significant. Another issue that we need to worry about is how to sample. So depending on which type of chart you've selected for your SPC program, how you physically sample is an extremely important issue. Whether or not you need rational samples or not is something that you need to consider in your sampling plan. And then finally, world-class manufacturers understand the distribution of their individual measurements. So for example, does our process really use 6 sigma, or maybe does it use more sigmas because it follows a non-normal distribution? Most industrial data actually follow non-normal distributions. You're actually more likely to get data in one direction than another. So for example, if I have a specification on roundness of a gear, and perfectly round is 0. We can't get better than 0, although we would like our data to tend to cluster towards 0. On the other hand, how out of round could we get? We could get infinitely out of round. And so it's just physically natural that data is not going to follow normal distribution. So we should understand that, and we should be able to predict and model what our data looks like. So what kinds of actions can we take? First of all, we should verify our SPC assumptions. We should ask ourselves questions like, do we have adequate measurement systems, or is there too much noise in our measurement system? Are we looking at the right characteristics that really are predictive of product performance? Are we using the most appropriate kinds of control charts for our application? Do we have appropriate sample sizes to detect the kinds of changes that are important? And what kind of data distribution does our data follow? We should also be educating operators and engineers so that they can take advantage of these tools. And then finally, we're going to need to leverage automated tools that can actually help us real-time monitor processes, so things like automated gauging and real-time statistical process control software. Now, getting back to our 5 practical steps, we move into step 3. And step 3 is minimizing variation. I'm going to start out by asking a question, and that is, if we had an industrial process and all of the products coming off the line were identical, then in theory, when should they all fail? And of course, the answer is pretty much at the same time. Now, a lot of times people will argue, well, they're not going to fail at the same time because customers use them differently and so on and so forth. But in our experience, when we go into manufacturing plants and pull a bunch of parts right off the line, take them into a lab and test them to failure, we see that they fail at dramatically different times, which is very surprising. We may get one unit failing at 100 cycles, and yet the next unit off the line is not failing till over 100,000 cycles. So the question is, why the variation in performance? I would argue it's because variation in the components. Also, in our experience, we've been looking at data and products for over 20 years, over 90% of failed products actually meet specifications. So, you know, we should have a good design to begin with, but if we don't have a good design, we can always protect ourselves by minimizing variation, because at least if we minimize variation, then if we know when one product is going to fail, we can pretty well predict when they're all going to fail. So at this point, I want to thank you, and I want to turn it over to Frank, who is going to pick up talking about minimizing variation.
Thanks, Allise. Good afternoon, everyone, and I appreciate you joining our webinar today. I would like to briefly talk about how to effectively minimize variation. It's been my experience that companies that are continuously reducing variation focus on 3 key things. The first is real-time monitoring and alarming. They, in general, push their data collection activities down to the shop floor as close to production as they can, and this usually involves some type of automation on their part. The second item is visualization for operators and supervisors. They typically provide immediate feedback to everyone, but in particular to those who are in a position to do something and who can react quickly. And the third item has to do with investigating variation, looking for areas where they can reduce variation and prioritizing their opportunities. Again, automation is usually the key to helping them do this. Let's start with the monitoring the processes in real time. Many companies try to do this with a paper and pencil approach, but quickly realize that it doesn't provide the feedback loops or the improvements that they were striving for. Plus, it can be cumbersome and time-consuming for someone outside of the department to analyze or even look at the data. Instead, the companies focus on using real-time monitoring by using software on the factory floor that can collect data from a variety of production devices, including PLCs, CNCs, micrometers, calipers, scales, and other sources of gauges and equipment. An example of this would be the screenshot from our WinSPC product that you currently are looking at. And although I'll be showing you screenshots from WinSPC in this presentation, all of the points that I'm making are relevant to any collection and monitoring system. The second reason that these companies use software is to help them better detect trends and special causes. A real-time monitoring system uses statistics to identify excessive variation well before the weight or the length or whatever characteristic you're monitoring goes out of control. These companies focus on preventing their processes from making bad product in the first place. One of the big advantages of an automated system is that once a statistical trend or anomaly is detected, it can alarm individuals in a variety of ways, from a simple message box to flashing lights to an email message, or to even very complicated commands that might signal a line to shut down or reduce the feed of an ingredient. The majority of the time, these alarms are meant to trigger some kind of human intervention. And as I've already mentioned, one of the key steps to minimizing variation is to alert those who are in position to react quickly to problems. Often, these alarms are intended for the operators, or your first line of defense. They're usually the ones who can react the quickest and take the appropriate corrective actions. An automated system should be able to alarm users of problems, guide them through the corrective action process, and document their activities. So this helps enforce accountability and provides data for a much broader analysis later on. The second item was visualization. And typical manufacturing plant, there are hundreds of characteristics to monitor. The operators are usually focused on just a few, and only the ones that impact their operations or their line in production. To identify broader sources of variation, managers usually use some type of plant-wide or summary view. With a dashboard-style view, problems become immediately visible, making rapid response a much more likely outcome. The last item that companies focus on is investigating and prioritizing quality improvement efforts. They start by taking all of their historical data from their real-time monitoring systems and search for excessive variation. The goal here is to uncover and expose opportunities that would have otherwise gone unnoticed. One of my customers is in the food packaging industry, and they make thousands of different packages across different product lines. And they were able to analyze their historical data, not by product or by process, but instead by fill heads and operators. And they identified a situation where several operators were making adjustments to the line that ended up causing more variation, not less. It's this type of investigation that companies who are trying to minimize do on a regular basis. At a minimum, they can answer questions such as which processes have the most variability or which processes changed recently. Ideally, they would like to answer questions like which processes have the highest cost due to variability. In fact, that last question is probably one of the most important ones on this slide, especially when it comes to prioritizing your activities. These companies try to focus their time and efforts on those areas that will give them the biggest bang for their buck. To help answer that last question, let me show you a tool that's being introduced in WinSPC version 8 called the Cost Inspector. And in fact, if I could just take a step back for a moment, I'd like to point out that the tagline for this webinar is how to make the highest quality product for the lowest possible cost. In order to do that, you first have to know what your costs are and how variability contributes to those costs. Likewise, not all scrap or rework or giveaway is treated equally. A small amount of variability, which causes giveaway of a very expensive ingredient, might be more costly than, say, a larger variation with a less expensive material in your raw materials. What this cost inspector does is shows me how you might be able to reduce my variability by a certain percentage, say 10 or 20 or even 50%, and what the cost savings could be. So as an example, looking at the blow-up here, if I was able to reduce my variation by 50%, I would save $141,000 or so for every million parts produced. This chart not only tells me how much money I could save, but it helps me prioritize my cost-saving efforts, which dovetails into a report something like this, where I'm listing all of my variables and how much I could save if I could reduce or eliminate variation from my process. This is the type of report that helps me prioritize or identify where I should focus my quality efforts. Companies that effectively minimize variation start by automating their data collection activities, and they push them down to as close to the production environment as possible. Second, they provide tools to the people who are in a position to quickly react and take action whenever an alarm or a violation is triggered. And finally, all of this data is available to them to search and uncover and prioritize their opportunities of not only reducing variation, but also reducing costs. All right, I'm going to hand the reins over to Steve, who's going to talk about the importance of optimizing your product designs and your processes. Steve?
Thanks, Frank. Good afternoon, everybody. I'd like to talk about the fourth practical step, which is understanding and specifically optimizing product designs and processes. And the reason this is so important is that in order to have, we've been talking a lot about SPC, but a key enabler for SPC is, number one, having a robust design, so we can use optimization techniques to develop robust designs. And secondly, for SPC, we need to make sure we have good process understanding so that we're knowing exactly what to control and how much variation we can tolerate without impacting product performance. Now, talking about optimizing processes or products, we have to recognize that all products must jointly satisfy multiple performance requirements And typically, in most of the projects we work on, trade-offs do exist. So in other words, if we try to optimize one performance requirement, typically we may negatively impact other performance requirements. And so what's required is taking into account all responses, all relevant responses, and using techniques like multi-response optimization, which use or leverage predictive models to help us hone in on the sweet spot or optimal places in order to run the process or optimal design specifications to meet all requirements. Now, in order to optimize, we first need that critical process understanding. So how do we get that understanding? Probably the most efficient method for developing process understanding is design of experiments, or DOE. And what DOE allows us to do is to develop these mathematical or predictive models based on physical testing. So essentially we run some trials or experiments where we vary factors that we believe affect our important characteristics, which we'll call responses. And from that data that we get, we can develop predictive models. I want to just briefly describe a simple example of using DOE for process optimization. This is a case where the objective, there was a need to reduce cycle time to produce an automotive window system where essentially we're molding a piece of glass and a rubber seal around the glass. And the purpose of the project, the objective was to reduce the cycle time by 1/2. So it was a pretty dramatic reduction. The problem arose in that by reducing the cycle time, the only way to get the appropriate bond strength was to dramatically increase temperature during the process. And by doing so, we introduced another problem, which was a greater distortion in the glass. So clearly there's a trade-off between distortion and bond strength, two critical characteristics of the process. Using DOE, we can conduct an experiment. And again, the outcome is a predictive model for all of the relevant responses, in this case distortion and bond strength. And we use that model to understand and quantify the relationships between the critical factors as well as interactions between those factors. I'd like to take just a second and show you an example of a predictive model, which is the output of a good DOE. And specifically, here's an example of a model for the distortion response. So this is just one of the two responses that we're mainly interested in. And what the model describes is simply the mathematical effect that each of our factors that we investigated, such as glass temperature and mold temperature, as well as their interactions, the effect that they have on the response, the distortion response. Now, clearly, in this case, distortion is bad, so we would like a solution which minimizes this particular response. We would also develop a second model based on other responses, such as bond strength. In that case, we would want to maximize the bond strength. Now, working with these models may be fun or tedious, depending on your joy with calculus or algebra. I'll assume most of you would prefer not to revisit calculus. So, fortunately, with the software available today, there are many visualization tools and techniques. This is an example of a contour plot, which essentially allows us to interpret the model graphically. And what we see here are different colors that exhibit or show regions of constant response ranges. So, for example, the blue region off to the left of this picture, if you can read the legend, and you can blow this up on your screen if you need to, represents a range of distortion of about 0.202 to 0.234. So everywhere where that shade of blue that's on the left-hand side stretches across predicts a response within that range for various combinations of two factors. That would be mold temperature along the x-axis and glass temperature along the y. Now, there were some other factors that affected distortion, and in this case, we're holding those, and those are indicated as hold values on the right-hand side. Now, this picture gives us a lot of useful information that might be difficult to glean from the model itself. For example, we can see the effect of changing mold temperature while glass temperature is fixed, or vice versa. For example, if we look at the effect of changing glass temperature when mold temperature is held near its low level, say 55 degrees, the effect of glass temperature is almost negligible, or really does not ever get out of that blue region. So it's very insensitive to changes. Distortion is very insensitive to changes in glass temperature. On the other hand, when mold temperature is high, we see a tremendous change in the distortion as glass temperature increases. So clearly, if we have a high mold temperature and we start increasing glass temperature, we're going to have some problems with distortion. Now, again, this system would be difficult to understand a model without a tool like design of experiments, so that's where the power of DOE comes in. Just remember that this picture just relates to one single response. We would also, in a DOE, also look at other responses. For example, we'd have a model for bond strength and a picture for bond strength. Next, how do we put all this together and jointly or simultaneously optimize all of the important responses? Again, in this case, we're going to have multiple models. I'm going to go back to another graphical technique which allows us to look across all of the models. Actually, in this case, there were 3 responses. One's distortion, and there were 2 different bond strengths we're looking at. And what this picture shows me is combinations of glue thickness and mold temperature in the white region there, given that we're holding the other 3 factors fixed, that would allow me to meet the requirements that I've specified for all 3 responses. So this is the so-called sweet spot for this particular process. Now, in a regular DOE, the responses can be really anything of importance, such as reliability targets, material requirements, dimensional requirements. It's very important when you're trying to optimize a system to think about all the relevant characteristics, even if they're not causing a problem, because as we optimize a process or a design, we're going to potentially be making some changes that could impact things that are not a problem today. It's critical that we optimize the system rather than individual features. To sum up, I'd just like to summarize some actions that I recommend you take when it comes to process optimization. Number 1, leverage DOE. It's a powerful tool to learn and optimize efficiently. While DOE has often been used historically in problem solving, it should be used more frequently and is used by progressive companies proactively, both in product design and in new process design. And there's just one other comment. DOE is a kind of a big field, and we recommend that when it is implemented, it's implemented in a phased approach. What I mean by that is when you're first starting the investigation effort, we want to make use of very efficient designs that allow us to look at many factors efficiently. So we might use designs like fractional factorials to do that. As we progress in the subsequent phases into knowledge building and optimization, we're going to use more robust designs or more extensive designs that allow us to get a better understanding of the response surface. And finally, there are many specialized types of experiments that may be required for specific issues such as designing new formulations or mixtures. And in those cases, there are severe constraints on the factors due to the relationship between levels of a formulation or components of a blend. Okay, with that, I'd like to turn it over to Frank, who's going to finish up with managing for the long term.
Thanks, Steve. Up until this point, we've been talking about specific activities that you could do to improve quality and reduce cost. But the companies that are most successful doing this focus on long-term investments. And to classify several long-term investments, starting with research and development, they focus on quality at the front end and build quality into their product designs. They also create feedback loops between production and R&D to drive improvement in their product designs. They also invest in education. Today we touched on a few applications of statistical methods, but it's a very large discipline that we haven't really done justice to. By mastering more advanced statistical topics, in many cases require expert instruction, which is why we've teamed up with Integral Concepts, who are skilled and well-versed in this area. And they also focus on the best approaches of SPC, which is widespread education of SPC fundamental concepts. Developing deep process understanding with training in statistical methods. These companies begin undertaking some very crucial steps that in some cases focuses or requires them to do a rethinking of their current practices. And they identify key characteristics which may impact performance, and addressing long-term problems or finding root causes. It's not always a straightforward task. It's a process of discovery that in many cases takes time and takes resources. They also invest in technology for prevention. There are so many different technologies that allow us to gain insight into our data and processes. And again, we've only touched on a few today. But the point is that leveraging technology is a necessary part on the road to high quality and prevention of problems. And continuous improvement, which all of the steps above are part of a continuous improvement program, but they also include clear improvement goals and agreed upon benchmarks. From an executive point of view, all of these investments require some type of executive level commitment to quality. And today, it's widely accepted there's a direct link between quality and customer satisfaction and profitability. But what isn't widely understood is that an investment in quality also reduces cost. To secure executive support, we need to translate our traditional statistical measures into dollars and cents, into cost savings. And here's an example of a very common process variation report by part and variable. And it shows some common statistics that are used to track variability, such as CPK and CP and sigma and so on. But the one big differentiator on this report is the very last column, which is a cost per million metric. Here I can see at a glance that I've saved $126,000 from last quarter based simply on a reduction in variation on my parts per million metric. This is the type of report that executives can look at to see that your quality improvement activities are bearing fruit. And likewise, if I look at the bottom of this report, I can see that from quarter to quarter I've actually had some increased variation in wall thickness, and it's costing me a little bit of money. This report can also be used to rank my priorities for quality improvement for next quarter. Here's another one called a cost improvement report, which shows a year-over-year savings on a per unit basis. And if I look at the third grouping there, bottle number 2's fill weight, I can see that I've saved on average 2.5 cents per unit, which might not seem like a lot to you and I, but in a high-speed bottling plant that makes 100 million bottles a year or so, this is a net savings of 2.5 million. So it's cost improvement reports like this that executives are keying in on. I'm a big believer in quality, and I think everyone should promote quality for the long-term investments, such as in R&D, education, and continuous improvement activities. The best way to promote these activities is to quantify your cost savings, document improvements, and translate statistics into dollars and cents. To summarize, I'd just like to take a moment here to review the 5 points of this webinar. And these steps aren't groundbreaking in any sense. Most of you probably are already familiar with some of these points. But they represent a basic practice that can be transformational if diligently applied. Companies that produce the highest quality product at the lowest cost focus on prevention activities using DOE and robust designs and real-time SPC. They apply the proper statistical methods and invest in SPC education. They emphasize the act of minimizing variation using real-time SPC and alarms and exposing opportunities. And they also use model and visualization tools to optimize and continue to optimize their processes. And lastly, they focus on long-term value, investing in R&D, training, securing executive support by reporting or translating your quality statistics into dollars and cents. These are all characteristics of companies that improve their quality, achieve the highest level of quality by reducing their costs. Hopefully you were able to take an idea or two away from this webinar and use it to improve your own quality systems. And if anyone would like more information on either real-time SPC or how to incorporate cost into your report, please feel free to contact me. My name is Frank Tappan. I'm with WinSPC, and you can either visit us at our website or contact us at the phone number or the email that's listed. If you have specific questions about advanced problem-solving techniques or advanced education topics, I'd ask that you contact Allise or Steve at Integral Concepts. Again, their contact information is also on this web page. And at this point, we're going to open up the webinar for question and answers. And I'd just like to take a quick minute, though, to thank everybody for attending, and I appreciate your time.
Great. Thank you, Frank. And now let's address some questions that have been submitted throughout the program. First, let's see. What is the number one preventable quality mistake that you see in the field?
Hi, Maggie. This is Allise. I'll take that.
Okay.
In our experience, the number one preventable quality issue is variation. There's excessive variation, even in such a way that the products are meeting spec, but because so much variation exists, there's very inconsistent performance, and as a result, market share losses, customer complaints, and everything we talked about.
Okay. All right. And what do you do if your SPC system needs to be automated, but your upper management team does not support the cost increase?
This is Frank from WinSPC. That is probably the point of my last section there, and I think that where quality engineers and quality managers could do a better job is translating their quality statistics into cost, into dollars and cents. If you can document, if you can show your executives on paper that by investing, say, $10 in this solution, I'll save $100, or investing $10,000 in this solution, I'll save $100,000. I think that is where the rubber meets the road, and common sense is going to prevail. Your executives are going to give you the funding that you need to hopefully purchase your SPC system and do some automation.
Okay, great. I believe this question is for Allise. In control can be out for both central tendency and suspension. The charts shown seem to indicate only central tendency. Can you comment on that, Allise?
Sure, yes. Basically, he's right. They can show, the SPC charts actually show two things. Number one, they show when a process either shifts, so the entire process average goes up or down by, a practically significant amount. So that's one thing they do. But more importantly, the asker of the question would be correct about, more importantly, these SPC charts show increases or decreases or constancy in variation. And really, I would say that's the biggest benefit of SPC, is that if the variability in the process grows, an adequate SPC system is going to catch that. So yes, SPC is designed to detect both changes in a process average and changes in variability.
Okay, great. Could one of you talk a little bit more about dealing with non-normal distributions? The speaker said, the question answer says, when most people assume distributions are usually normal. Yes.
This is Allise again, an excellent question. It is true that most analyzers assume normality of the data. They assume that the data follows a bell-shaped curve. And as a result, the estimates that we make, when the predictions that we make, are very often way off. So the issue is if the data isn't normal, and unfortunately most industrial data actually isn't bell-shaped. Now some is, but much, if not, the vast majority is not normally distributed. So there are a couple of very common techniques that we can use to handle non-normal data. The first technique that we can use is called distribution fitting. And what I mean by that is if the curve that describes the data isn't a bell, let's find out what kind of a curve or function does describe our data. So very common distributions or functions would be, for example, log normal is a very common distribution that describes how our data distributes itself. Another real common one would be Weibull or log logistic. So anyway, these are common distributions that describe our data, and that's one way. We can just simply model it and then make predictions. The other way of handling non-normal data is you say, you know what, my data's not normal, so I'm going to make it normal. And how you do that is through what are called data transformations. So, for example, my original data, let's say I've got leak rate data. My leak rate data might not follow a bell-shaped curve, but if I take the natural log or even the log base E of every single number, those data might follow a bell-shaped curve. And then as long as I transform the other things that I'm looking at, like specification limits or whatever, then I'll be okay. So there were two basic strategies. One is to distribution fit, find a curve that describes, and the second would be transform the data and make it normal. I hope that answers the question.
Great. I believe this is for Frank. Where do you traditionally see the biggest cost areas, and where should we look first? And is there a biggest bang for your buck approach?
Traditionally we focus on variation within the plant floor, so variation in production line. That's where we see the biggest cost savings. But to get the biggest bang for your buck, so to speak, or some of the, low-hanging fruit to focus on is making sure that your process is on target. In many cases, we go in and look at the data from our cost inspector's point of view, and we see that the process isn't targeted or it isn't at the optimal mean. And because it's not at the optimal mean, you're costing yourself money. Shifting your process to that optimal mean is usually a very simple task. and it's usually one of the easiest things that you can do to reduce your costs and the bottom line, save money.
Okay, terrific. What are some good products for performing DOE?
This is Allise. Good products for performing DOE. I mean, first of all, the biggest issue is really in the design and planning of the DOE. I know software is important, but there's a lot of good software that can be used for DOE. So, for example, DOE++ would be an excellent package. JMP Jump is probably a premier package. Minitab. I mean, design expert. There are lots and lots of packages that can be used. The more important issue in successful application of DOE is really to understand what kind of design we need, which factors to put in, how to set those factors, how to develop the predictive models. So I would say more importantly than the software would be the understanding of how to properly design, apply, and analyze and interpret. But there are lots of great statistics packages out there.
Perfect. Okay. And can one of you provide an example of using a model to determine process performance? I see where it aids in process performance.
Yes, absolutely. That's an excellent question because mostly what we were talking about in this discussion was predicting product performance, but models can actually be used to predict process performance as well. So let's pretend that I've got a manufacturing line, and as an intermediary step, I need to control the viscosity of something. Viscosity might not be a final product characteristic, but it is intermittent. There's something intermediary. So basically what I can do is figure out what kinds of input variables, production settings and things like that control viscosity, or things like coatings or active ingredient weight or particle size or steel tensile strength. So we can actually develop models for processing that actually predict process outcomes as well. And actually we do that very, very commonly.
Great. The next attendee asks, we are a high-mix, low-volume assembly and test operation. We test 100% of our finished product. Is SPC applicable?
Maggie, did you say high volume, low mix, or just the opposite?
High mix, low volume.
Oh, high mix, low volume. Okay. Basically what they need is they need short production run SPC. So bottom line is that SPC is absolutely applicable. What they want to do is they want to monitor their processes, not the products that they're making. And I think even Frank may have alluded to that in the webinar. But basically, really all the concepts are the same. So let's suppose that as their production, one of the important features that they have to monitor is, let's say, a diameter. Now, their products are changing, and so the diameters are going to change, but basically what they're going to look at is how good is the process at hitting the right diameters. And they can use what are called standardized denom charts to do that. So that way, they can make extremely low volumes and high mix and really just focus on the characteristics that matter and just have an SPC chart, let's say, for diameter, regardless of the product that they're making.
Terrific. Does WinSPC have traceability capabilities?
Yes, we do. We have traceability. We call them tags, and we have an unlimited number of tags that you can assign and use those tags to actually track your material all the way from incoming inspection through your different processes all the way to finished goods.
Okay, terrific. This question is for Allise. Allise, do you believe that process variation monitoring and in-process monitoring on 100% of parts can be used together?
Hi, Maggie. Yes, I do believe they can be used together, although I would say that if we really have a very good SPC plan in the production area, and we have the right sample sizes, the right charts, and the right sampling plan, and so on and so forth, that hopefully we wouldn't even need the 100% online monitoring at the very, very end. But there's no conflict to using both. There's no conflict whatsoever.
Okay, terrific. I work for a contract manufacturer that loads circuit boards. Therefore, we really don't use variables data. What is the best SPC method for prevention when using attribute data?
This is Allise again, Maggie. Basically, there were lots of attribute charts. The most common ones are monitoring proportion defective, or if volumes change dramatically, standardized proportions defective. We can monitor count data. We can monitor standard count data. For example, we could monitor, let's say, number of solder joint issues per 1,000 boards or whatever. So there are lots of charts that are developed for attribute data.
Terrific. I think we have time for, let's do 2 more questions. What is the best method for SPC data collection for custom-made-to-order products?
For custom-made-to-order products, it sounds, again, like possibly a short-run SPC technique. I guess it depends on the volume of data that you're capturing. That's a question that I would really need to know more information, and I guess I would invite whoever asked that particular question to either contact me directly or register at our website. This is Frank, by the way, speaking from WinSPC.
All right. Okay, and this is a short question for Allise. Allise, do you still recommend the book Statistics for Experimenters by George Wachs, or have you found a better book?
Oh, no, that's still the holy grail. I love Fox Hunter and Hunter. It's an excellent book. There have been other very good books written on design of experiments, though. Douglas Montgomery's written a great book. There are lots of great books out there, but Fox Hunter and Hunter is still a classic. It's an excellent book.
Terrific. We still have plenty of other questions that were unanswered. If you have more questions for Allise or Steve or Frank, you can contact them with the emails provided on that last slide during the presentation. So this concludes today's webinar. Please join me in thanking Allise, Stephen, and Frank for a great presentation, as well as our sponsors, DataNet, Integral Concepts, and WinSPC. As you exit today's webinar, please take a few moments to complete our survey. We strongly welcome your detailed comments, and this helps us serve you better. If you have any additional questions or comments, you can also contact me directly at mcfaddenm@bnpmedia.com. We appreciate your time and hope you have found this webinar to be a valuable experience. Thank you.